Hey, good afternoon. Today's video is on GPower in the context of regression analysis. My name is Christian DeLucia, and I'm a professor in the Department of Clinical and School Psychology at Nova Southeastern University. And I also want to acknowledge contributions to today's video from a current grad student here. His name is Ali Tabacoli. So a few learning objectives for today's video. You're going to learn about statistical power and the probability of type 2 errors, how to conceptualize power in several scenarios commonly encountered in regression models, how to quantify several quantities of interest like r squared, 1 minus r squared, and f squared, and of course, how to use GPower to figure out sample size requirements for a study you're hoping to conduct. Currently, I have one related video. It's a basic how-to video for running a linear regression model. I talk about some concepts in that video that are relevant to today's video as well. I plan on shooting an additional video on incremental variance and hierarchical regression. Both of those concepts are relevant to today's discussion, so look for that in the future. Okay, GPower is a free software that can be used to power various statistical analyses. In this video, I'm going to limit my discussion to GPower in the context of multiple regression models. And the video is meant to be a basic how-to, but a number of more technical elements are discussed. For viewers with less familiarity with regression, feel free to gloss over the technical elements and just focus on the sort of how to run the models. Statistical power is the probability of detecting an effect if one exists in the population. There are a lot of different ways you can say that, but this is a sort of common definition that you'll see in a stats text or a research methods text. If you fail to detect an effect that exists in the population, you've made a type 2 error, which is typically denoted by the symbol beta. Power and the probability of type 2 errors are complementary probabilities, so they sum to 1.0. That means that you could compute power as 1 minus beta. Historically, the industry standard for power in the social sciences has been 0.8, which implies a type 2 error risk of 1 minus 0.8 or 0.2. In that case, you would say the beta risk is 0.2 or 20%. Obviously, if you're interested in a higher level of power, you could use the software to achieve sample size requirements for any given level of power you're interested in. Okay, now researchers are interested in statistical power across the whole research cycle, but there are some extra incentives at the study planning phase when you're doing things like writing grants to try and secure funding to conduct studies. In those instances, the granting agencies are often interested in power computations because they want to know that you're going to have adequately powered statistical tests to test your primary study hypotheses. Otherwise, they're worried about not getting a good return on their investment in your research. A couple effects of interest in the context of regression models. We're going to talk about testing the significance of an overall model. We're also going to talk about testing the significance of a set of predictive variables over a base model. And both of these tests are relevant to this concept of incremental variance. Okay. The topic of incremental variance is a, it's a big topic and it's nuanced in its own right. I'm not going to really get into the specifics. For today's talk, I'm gonna quantify a couple of relevant quantities, and we'll just work with those. And the concepts can be generalized to other scenarios, and basic stats texts on multiple regression talk about incremental variance and various um, quantities that are relevant. So I have a couple references that will talk about these quantities that you could look at if interested. Okay. Now the effect size that GPower uses for its power procedures in regression is Cohen's F squared. Okay, so I want to talk a little bit about how we compute Cohen's F squared. I have a generic formula for it here that I will make a little bit more specific to our examples um, as they unfold here in the video. So in the numerator of the formula, we've got r squared change. Okay, in the denominator, we've got 1 minus r squared. And um, the numerator can be thought of as the incremental variance associated with the model in question. That can be the overall model. That can be the addition of a single predictor over a base model. That can be the addition of a predictor block that has 3 predictors over a base model. So we have some flexibility there. And then the denominator is the residual variability or the variability left in y after you've taken into consideration the model or the predictors in question. Okay, so F squared forms a ratio of incremental variance to residual variance. Okay. Now, the first example that we're going to look at is testing an overall model with 3 predictor variables. And so my F squared equation on this slide is a little bit more specific to the current scenario. We could read the numerator as r squared sub y dot a3. And we're just saying that it's going to be the r squared in y, or the proportion outcome variability in y, that can be attributed to predictor set A, and the number 3 there suggests that A has 3 predictors associated with it. So we have some precision associated with the notation. In the denominator, we've got the residual variability, or 1 minus r squared y dot A3, and my notation system is adapted from Cohen's 1988 text on statistical power analysis. Now, on this slide, I show the basic GPower setup. So we're going to make 3 selections to get started. Under test family, we're going to select F tests. Under statistical test, we're going to select the highlighted option, which is linear multiple regression, fixed model, r squared deviation from 0. And then under type of power analysis, we're going to select a priori. And there are a couple different options there, but a priori is what you would use during the study planning phase. Okay. Now, most power programs, and GPower is no exception, have some input parameters that are required. So the user has to specify various inputs. And then based on those inputs, the program will generate some outputs. And so we'll look at the specifics in terms of the outputs in a second. So if we just look at the inputs here, GPower is asking for F squared, which is the effect size estimate. It's asking for the alpha or error probability. It's typical to use 0.05 in the social sciences. It's also asking for the level of desired power. So I put in 0.8 and the number of predictors associated with the model, which is 3 in this case. Okay. At the bottom on the left-hand side here, I show how we would compute F squared directly from the r squared that we're hoping to achieve. So here we're conjecturing that the model with 3 predictors is going to account for 15.6% of incremental variance in y, and then the denominator would be 1 minus 0.156, and then if we form that ratio, we get the F squared of 0.1848. If we hit calculate, GPower will generate the outputs. And I'm going to draw your attention to total sample size, which in this case is 64. So essentially, GPower is telling us that given the inputs that we provided, we're going to need a sample size of 64 to have adequate power to detect the r squared, F squared that we specified. Okay. Now, in our second example, we're going to test the incremental variance associated with predictor set B over predictor set A. Now, for those of you familiar with the concept of hierarchical regression analysis, you'll recognize this example. This is a case where we have an initial model, predictor set A, which has 3 predictors in it, and then we want to test for the incremental variance of 2 additional predictors. And so in order to power this analysis, we're going to select a slightly different option under statistical test. We're going to go to linear multiple regression, fixed model, R-square increase. Okay, all other general selections are consistent with example 1. Now, if we look at our inputs, we've got some slightly different inputs there. So GPower is asking for f squared, and I'll show you how to compute that in a second. It's asking for the alpha level, 0.05, desired level of power, 0.8. The number of tested predictors is the number of predictors in set B, and then the total number of predictors would be total over sets A and B combined. Okay. Now the formula at the bottom of the slide on the left shows us how we could compute the f squared. So in this case, we're conjecturing that the overall model will account for 40.2% of outcome variance. And then we're also conjecturing that predictor set A accounted for 15.6%. So that would leave our R-squared change of 0.246 for predictor set B. And then our residual variability in the denominator would be 1 minus 0.402. Okay, so if we solve that equation, we could enter the f squared of 0.4114 on the input side. If we click calculate, GPower will generate the outputs for us. And again, I'm going to draw your attention to the total sample size, which is 28 in this case. Now, because the R-squared change is 0.246, suggesting that 2 predictors account for 24.6% of incremental variance over predictor set A, the effect is pretty large, so the sample size requirement is less formidable in this case. Okay, now in our third scenario, we're going to test the significance of predictor set C, which also has 2 predictors. We're going to use the same procedure we used in example 2. We have to change the inputs somewhat. We're going to compute Cohen's f squared as 0.1262. I'll talk a little bit more about that in a second. We're going to leave the alpha level at 0.05, desired level of power at 0.8. Number of tested predictors in this case is 2 because predictor set C has 2 predictors in it. And then the total number of predictors is 7. And in this case, that's going to be the full model. So we could compute f squared directly by taking the r squared for the overall model, which we're conjecturing is going to be 0.4690. We're going to subtract away the r squared for the first 2 predictor sets. Again, we're conjecturing that that was 0.4020. And then in the denominator, we're going to put the residual variability, or 1 minus 0.4690. If we solve that ratio, we end up with the f squared of 0.1262, which we enter directly in the inputs. Okay. Now, GPower will generate the outputs for us, and the total sample size requirement here is going to be 80. So that's telling us that our R-squared change of 0.067, given our inputs, will require a sample size of 80 to have power at 0.8. Okay. Now, in our final example, example 4, we're going to test the significance of a single predictor from the final model over the remaining predictors in the model. Okay, so I set up the f squared here by, in the numerator, I've labeled a set E with 6 predictors and a set F with 1 predictor. So R squared overall is going to be the full model minus the R squared associated with the model with the 6 other predictors, not the one being tested. Okay, the denominator is residual variability. And so the estimates that we're working with in this case are 0.471 for the full model, 0.434 um, for the R squared associated with the first set of 6 predictors, and then the residual variability is going to be 1 minus 0.471. That's going to give us an F squared of 0.07. So we're going to put that in inputs. We're going to make the other changes as relevant. So in this case, we're testing a single predictor, and the total model has 7 predictors in it. If we hit calculate, GPower is going to generate our sample size, which in this case is 115. So that's telling us to detect an R squared change of 0.037, or 3.7% of incremental variance associated with a single predictor over a base model with 6 predictors. We need 115 participants in order to have power equal to 0.80. So here's a summary of the power analyses that I just walked you through, examples 1 through 4 with F squared and N tabulated. We can see here that our sample size requirements range from a low of 28 to a high of 115. And when you're doing these kinds of analyses in the study planning phase and you've got a set of related analyses, you would just take the sample size that is the maximum to ensure that you're adequately powered across the full set of analyses. Oh, I guess I should mention, if you want to adjust for the possibility of attrition, you could use a pretty simple formula. In this case, if we assume 10% attrition, but we want to end up with a sample size of 115, we've got to figure out that 115 is 90% of 128, essentially. So we would recruit 128 participants, and if we retain them all, we're adequately powered, and if we lose 10% of them, we remain adequately powered. Of course, if we lose 15 or 20%, then we start to the power associated with the analysis starts to decay, relatively speaking. Okay, now we can also, in all of the original 4 examples, we computed the F square ourselves and then input it directly into the GPower inputs, and allow GPower to generate the sample size estimates based on that. Now, there are a few other procedures you could use within GPower where it will compute Cohen's F squared for you, given the model you're setting up. And so I'm going to show you 3 ways of doing it. One is from the overall R squared. The second way is from the predictor correlations. And the third way is from various variance estimates. Okay, so if we want to compute F squared from R squared, we can click on determine, and GPower will open up this other window, and then it'll give us a couple options here. So if we check on from correlation coefficient, we could enter the squared multiple correlation directly. In this case, we conjectured it was 0.156. So once you make that entry, if you click on calculate and transfer to main window, GPower will put the F squared over here. And then, the other selections are inputs that you made. And then if you click calculate, GPower will generate the power estimate for you. This is the setup from example 1 from up above. Okay, now if we want to generate F squared from the predictor correlations again, we can click on determine under input parameters. GPower will open this window on the right-hand side. If we click on from predictor correlations and then click specify matrices, GPower is going to ask us to provide entries for 2 matrices. One of the matrices gives each pairwise correlation between each X and Y. Now, GPower labels the predictive variables, which are generically referred to in the context of regression analysis as the X's. It labels them with the letter P for predictor, right? So P1, P2, P3 equals X1, X2, X3. And then the other matrix that GPower will ask for entries for is the correlations among the X's or among the predictive variables. And so here's the 3x3 correlation matrix. Obviously, you need some prior data in order to have estimates for these, these various correlations. Okay, if we input this information, click OK, and then say calculate and transfer to main window, GPower will run the power analysis for us and give us the um, sample size requirement. Okay, in our last option here, we're going to compute F squared from variances. So we're going to click on, and this is for the scenario where we're using R square increase. And so if we click determine and check from variances, GPower is going to ask us for variance explained by special effect. That's going to be the R square change associated with the effect in question. And then it's going to ask us for residual variance, which is going to be 1 minus R squared model. And so these estimates are from our third scenario, I believe. And I'm not sure if that's true, but regardless, if we let W equal the variance explained by the special effect and we let Z equal residual variance, we can compute F squared as a ratio of W to Z. Okay, so in this case, it'll be 0.246 divided by 0.598, which will give us the F squared of 0.41137. Okay, and then SPSS will also generate the partial correlation. And the partial correlation, we could solve for that again by forming a ratio of W to Z plus W. Okay, and again, if you're, partial correlation, semi-partial correlation, zero order correlation, those are concepts that come up when we talk about multiple predictor models and we talk about incremental variance and unique variance associated with a predictor or a predictor block. So if you want to learn a little bit more about that, refer to the stats text in the reference list. Okay. Obviously, when you're running power analyses, coming up with the inputs is usually the hardest part. You also have to figure out the software or the syntax relevant. And so, you have to ask questions like how much incremental variance are predictors X4 and X5 going to account for over predictors X1 through 3. And sometimes it's a little easier to conjecture about those estimates. Sometimes it's a little harder. Pilot data, the prior literature can be helpful. Okay. My website is not up and running yet, but it will be soon, deluciastats.com. So visit the website to find this video, the source materials used to make it, other videos and other source materials, and you'll be able to download data files and run analyses from the videos and replicate the output that I discuss in the videos. Okay, some references, Cohen's classic 1988 text on statistical power analysis, the Cohen-West and Aiken test on multiple regression, which is sort of a classic text, and then a citation there for the GPower folks who for many years now have been providing this great free service available to researchers interested in conducting statistical power analysis. Thank you for watching. I hope you enjoyed the video and I hope you learned something about power analysis. Take care.